Hi, my name is Manuel Berkemeier. I'm a PhD student at Paderborn University in Germany, and today I want to talk a bit about the first project I undertook using the Julia language. The work I am presenting is a joint endeavor with Sebastian Peitz, also from Paderborn University, and we have developed a derivative-free local optimizer for multi-objective problems. It uses ideas from trust region algorithms, and our work has been funded by the European Union, more specifically by the European Regional Development Fund. First, let me provide you with a short outline how this talk is structured. I will start with giving you a motivation of why we choose to go with the trust region approach. I will then provide the basics of multi-objective optimization and continue by giving the definitions of descent directions in the multi-objective case and the notion of criticality. We will then come to the basic ideas of the trust region algorithm and a high-level abstraction, and you will finally see some Julia code there. I will then present some results from the paper we have published using our implementation, and finally discuss a bit about the history, the current state, and the future of the Julia package that resulted from our work. It's called Morbid. Now for the motivation. Why did we choose the trust region approach? Well, because we were faced with a problem where our objectives of an optimization problem were given by an expensive black box function. That is, this function we assume to be very costly to evaluate. It takes from seconds to minutes to perform one evaluation. And due to that, we also do not have access to the gradients and cannot approximate derivative information. In general, these functions take n real variables and provide us with k objectives f. Some examples, we could think of a driving simulation where we would like to optimize the driving behavior of a vehicle by configuring its speed, its acceleration, with the objectives being the travel time, the fuel consumption, but also the safety, of course. We could think of artificial neural networks and their inner weights as parameters, but also about problems involving finite element solvers. What do we mean when we say we have a multi-objective optimization problem? Well, we can first simply write it down. We say we want to minimize some objectives f1 to fk within a feasible subset mathcal x of Rn, and this problem we call MOP for multi-objective optimization problem. And like in single objective optimization, we have a very basic notion of a minimizer. We say that x star is a solution of MOP if there is no better point. And by that we mean there is no other feasible point x that is at least as good in all objectives and is better in at least one objective. And by better, of course, we mean it has a lower value because we are minimizing. And such a point where there is no other better point we call Pareto optimal or non-dominated. And usually for this kind of problem, you have multiple solutions, which are in a certain sense optimal trade-offs between the different objectives. And these solutions then form the so-called Pareto set and are mapped to the Pareto front in objective space. I come back to the driving example to better illustrate the optimality criteria. We assume that we have the two two objectives of minimizing the risk of a test drive and also minimizing the travel time. And now you can think of different driving behaviors. You can try to be very fast, but in consequence also drive very risky. You can have a slow but very safe vehicle. And of course, you can have a trade-off and be moderately fast, but also safe. And within this limited data set, all these points would be Pareto optimal, because in objective space, there is no other data point that is better in at least one objective and at least as good in all other objectives. Such a point would be to the lower left in objective space. Whereas if there would be another data point like this red one, this point would not be optimal, of course, because the driver would be too slow and drive too risky. The purple point would in all cases be better. And with this optimality condition and criteria, you can try to find some solutions. Like the easiest approach would be to simply spawn some points and then perform pairwise comparison in objective space. Like you can see here, the Pareto set has been approximated by the blue points. But of course, this approach can become very expensive. Like it has a quadratic complexity in the number of sample points, and you need more and more samples, the more decision variables n you have. Thus, we can ask ourselves, can we do better? Can we do something like in single objective optimization? Can we do, for example, gradient descent for MOP? And the answer is yes. To see how, we remember the single objective case SOP, and we remember one basic necessary condition for a local minimum. We know that if X star is a local minimum of SOP, then it is also critical. And by that we mean there is no descent direction D within Rn, where the projection of D onto the gradient at X star is negative. And else, if X was no minimum, we would have such a descent direction and could move a tiny bit along that descent direction and decrease F. For the multi-objective case, the situation is very similar. We have a definition that says if X star is Pareto optimal for MOP, then it is also Pareto critical. And by that we mean there's no direction D where the projection onto all gradients is negative. And else we could again move a tiny bit into that direction and decrease all objectives. And to summarize, the idea that we want to pursue in our algorithm is, as long as some point is not Pareto critical, we can find a descent direction and move along that direction. So we want to find these critical points, which are a superset of the Pareto set. Now there are two problems which we have to solve for our use case. First, our feasible set isn't unconstrained. We have a feasible set that is defined by finite box constraints. And in our theoretical part, we have shown we can work with any convexly and compact set, mathcal X. The second problem we have to solve is that by assumption, we have an expensive black box objective. So we have no gradient information, and we must form some surrogate models M and use them instead. So use the gradients of ML instead of FL. And combining these ideas and trying to solve these two issues led to the trust region framework I'm describing now on a very high level. The first step in each iteration would be to build such a surrogate model M of the true objectives near the current iterate. And we want these models MT to be accurate within the current trust region, which is usually a ball of radius delta around the current point xt. Then we test if the current point xt is critical for the surrogate models. And if so, we decrease the trust region radius and go back to step 1 to make the models more accurate. Elsewise, we try to find some approximate descent direction using the surrogate models. And of course, we also need some step length, and we can then define the trial point x plus along the descent direction. Finally, we have an acceptance test to test whether the trial point actually decreases the true objectives. We know that it decreases m, but does it decrease f? And if so, if there is sufficient positive decrease for f, we accept the trial point and maybe increase the trust region radius for the next iteration. Else, we reject the trial point and maybe shrink delta t. Now, of course, this is a high-level description of the algorithm. There are some more tricks to it. You have to be a bit careful how you shrink and grow the trust region radius. And of course, you would need a stopping criterion. For example, at a critical point, you would loop for an infinite number of times between steps 1 and 2. You should stop when your radius becomes too small, or you have a small radius and criticality for surrogate models. Within one iteration, the descent step for the surrogate models looks a bit like this. We are using the infinity norm for the trust region radius, such that the trust regions are boxes within the decision space, and we then compute the trial point such that there is a descent in objective space, as you can see on the right. I didn't specify how we compute a descent direction yet. And to do that, we combine the multi-objective steepest descent direction, as given by Flieger and others, and the projected gradient approach that is also found in single-value trust region methods for these kinds of constraints. And together, we get an optimization problem that looks like this, and we have to solve it in each iteration of our algorithm. It is a convex optimization problem by assumption on our feasible set. And it has 3 constraints, where the first constraint involves the surrogate Jacobian and ensures that we are actually computing a descent direction. The second constraint ensures boundedness and the existence of a unique solution. And the third constraint is due to the projection approach. And thanks to the JUMP project, we can also easily solve this problem in Julia. And I've written down how we do it in our package. I'm also using the OSQP solver for linear and quadratic problems, because using the infinity norm and box constraints makes this problem linear even. And we start by defining our problem as opt. We can then simply add the variables like we've done on the left. We add alpha, we add the container D, and we specify that we want to minimize alpha. We then specify the 3 constraints, like the descent constraint, the norm constraint, which I've rewritten a bit to make it an interval constraint, and the global box constraints if present. And we then can simply call optimize on our model and retrieve the descent direction. And in our package, we then continue with backtracking to find a step size. I also didn't say yet how we construct our surrogate models. We have several choices for these models. If gradient information is available, or you can do finite differences, then you would usually use linear or quadratic Taylor approximations for your objectives. You can also use quadratic Lagrange polynomials, like has been done in a multi-objective trust region algorithm already by Thomann and Eichfelder. But both these approaches have the drawback that if you want to use nonlinear models, you need a number of samples for construction and thus a number of evaluations that grows quadratically with the number of decision variables. And that is why we wanted to try radial basis function models. Wild has shown in his dissertation how you can construct these models using only in the vicinity of n samples and n expansive function evaluations. And these models have the additional benefit that you can add additional sampling points from a database at little cost to capture non-linear behavior as well. And these are scalar models, and we use k of them. They have a polynomial tail and a weighted sum of shifted radial functions. They are shifted around these center sides psi I, and they are called radial because they are radially symmetric around their centers. I've plotted the Gaussian kernel here in the one-dimensional case. And as you can see, some of these functions can be fine-tuned using an additional shape parameter. And all we have to do to construct these models is, after we've gathered the samples, solve a linear equation system. That is why we get these K models at little to no overhead. The difficult part is to generate the sampling data. You have to respect some geometric conditions there. Now, RBF models are already available in Julia. There's the great package surrogates JL, but I didn't know about it at first, and then later realized I also needed access to some internal data of these models. That is why we have our own package, which is already registered in the general registry. It's called radial basis function models, and you can install it and also use these models by first defining some training data, X and Y, and then providing the model constructor with your training data. And I've shown one of these models on the right-hand side, where you can see that the red line, our model, is able to capture the nonlinear function shown in blue very well within the limits of the data points. And evaluation is also simple. We provide several radial kernels. The framework and the package should be easily extendable. You get the derivatives, which we need, of course, in our algorithm as well. And we've also implemented a basic MLJ interface. And if you're interested, the documentation of that package details the construction of these models in a very theoretical way. Now, let me show you some results that we could show and obtain using this idea. Our main theoretical result was that we could show that if our feasible set is either unconstrained or it is compact and convex, then our algorithm converges to a Pareto critical point under some standard assumptions. For example, that our objectives are bounded from below. And I want to show you some iterations of the implementation. Coming back to an example you've already seen without knowing it. It is a two parabola example where you have two-dimensional parabolas centered around the points 1, 1 and -1, and where we know that the Pareto set is simply the line connecting the individual minima, and the Pareto front is convex. And I've let an early implementation of the algorithm run on this problem. And as you can see, we have descent for both objectives simultaneously. And now you see that some steps get rejected where we do not have sufficient decrease or even increase the true objective. I'm now going to show a more complicated example that I've taken from Thomann. There is only a single Pareto optimal point, and I've tested radial basis functions against second degree Lagrange polynomials. We only allowed up to 20 function evaluations, and you can see on the left-hand side that the radial functions were able to get to the minimum using only 12 evaluations, whereas the Lagrange polynomials used 19 evaluations and didn't find the minimum. And of course, we tested this on more complex and scalable problems with different starting points, and we showed that RBF were usually best in terms of the number of expensive evaluations, like you can see with the black line here. Now, finally, I want to talk a bit shortly about the journey that it has been to develop this package. First of all, MORBID is called MORBID because it's an acronym for multi-objective optimization by radial basis function interpolation in trust regions, to honor the single value optimization algorithm ORBIT by Wyatt, which greatly inspired me. And I started by having already done some work in this regard within MATLAB and Python. And as usually, I simply ported and rewrote the stuff in the Julia language by looking up the documentation. And as most beginners, I did it in a very Pythonic way, maybe, and object-oriented way. And I misused structs, for example. I used them like Python classes. I wrote long, complicated functions, and this all made it very hard to modify and extend the package, which is why, with the paper deadline coming due, I refactored the package for flexibility. I defined internal interfaces for nearly everything, which made it easily extendable. We can thereby provide different surrogate model types like Taylor and Lagrange polynomials, as well as the radial basis function models. And we can also use different descent methods, not only steepest descent. Moreover, we have access to the training data afterwards. Finally, if you want to use the package from within Python, we also wrote a Python wrapper to access and easily use the package. Lastly, what do we... Oh, sorry. I wanted to provide a usage example first. Like, it's very easy to use the package too. You define your objectives. You then set up a problem. You add your objectives and specify how you want them modeled. For example, I can provide a configuration to make it modeled by radial basis functions. I can then call optimize with a starting point and get an iteration, hopefully to the Pareto set, but at least to a critical point, I hope. What's up for the future? When I made this slide, I thought about how to list all the things I plan to do, and I decided to make them GitHub issues. So you can also see what I'm doing, and you can also see if I have done anything in the meantime until you see this video. Right at the moment, I'm refactoring the code again a bit to strongly type my types, because in my quest to keep everything as general as possible, I again ignored the performance tips and have things like the structs where every field is assigned to an abstract type, which of course isn't great for performance. There's some mathematical aspects I would like to integrate next, like general constraints, and maybe a possibility to reuse sampling data to find additional solutions along the Pareto set, but that's all up for the future, and great topics for future research. And if you'd like to be part of this package, don't hesitate to contact me. That's all for my talk, and I thank you for listening.